Welcome to lesson 12.3. Today we're going to look at tangent lines and velocity, but before we do that, let's review limits, and specifically in lesson 12.2, we didn't just review limits, we were looking at them algebraically. So I'm going to do algebraically, as well as you can see I have Desmos open on the left. I will go over what we did in lesson 12.1, which is seeing them graphically. So algebraically, we learned a few rules, specifically that when you evaluate a limit that's a polynomial function, this is polynomial. That means all powers are whole numbers, and none of the powers are negatives. So they're counting numbers, basically. And you might say, well, what about the 1 here? It doesn't have a power, and this x doesn't. Well, x is the same thing as x to the first, and just a number by itself. It's kind of like x to the 0. Whole numbers are the numbers from 0 counting up that are not decimals, not fractions, and positive. So this would be polynomial. So you could use direct substitution, which means to discover this limit, we would just plug in -2. So the limit would equal 1/2 times, instead of here x cubed, I'm going to change that to -2 cubed. I'm substituting in parentheses, especially, this is very important always, but especially when it's a negative, just because you use technology to make sure you get the correct solution. The technology will follow PEMDAS, and it could give you an incorrect solution if you do not place that negative right, or the parentheses around it. Okay, so that's what I would be directly substituting. In this particular case, -2 cubed means -2 times a -2 times a -2. 3 -2s, when you're multiplying, will end up with being a -8. So we have 1/2 times -8. -5 times a -2 will equal a +10 plus 1 more. And 1/2 of -8 is -4. So -4, and then 10 plus 1 is 11. So -4 plus 11 will end up equaling 7. So that's using direct substitution right there. We get this value 7. Now, if you wanted to see graphically, you would graph 1/2 x cubed minus 5x plus 1. We would take out this graph, and if you wanted to at the front, you could do like f of x equals, just like that. And you would be checking, what does this graph approach as what does the y value approach as the x value approaches -2? So from the left and the right, as we approach this value here of -2, you can see these are counting by ones. That's -5, so -1, -2. As we approach this value right there, you can see that both from the left side and the right side of this graph, we're approaching the y value 7. And if you want to check what the table, whoops, that's not what I meant to do, table like this, we want to approach -2. So I'll kind of get some numbers that are close to -2 here, -2.01, and we'll do one more, -2.001, -2, -1.99, -1.9. You can see how this, I missed one here, -1.999. You can see as we get closer and closer to that value -2, both from this would be the left side, this would be the right side. You can see the number we're approaching is that 7 rather. So that'd be the answer to -1, or number 1. Sorry, number 1 would be 7. All right, let's take a look at number 2. Now we're looking at a rational function. So rational is where you have a polynomial divided by another polynomial, and we learned we can use direct substitution on this, borrowing that when you plug in the 4, you're not dividing by 0. So I'm going to check that real quick. We'll have 4 minus 1, I'm sorry, over 4 squared. And here, I'm a positive number, so it's not as critical to put the parentheses, but I will still use parentheses. 2 times, substituting in 4, plus 3. That will not equal 0 because all these numbers are positive that are adding together. So certainly, that'll be a positive number. So let's just see what that equals when I simplify. I'll have 3 divided by 4 squared is 16. 4 times 4 is 16. Plus 2 times 4 would be 8. Then plus 3 more. So it looks like to me it'll be 3 over 16 plus 8 is 24. Plus 3 more is 27. And this can simplify. 3 goes into 27 9 times. So this would just be 1/9. So D would be the solution. Check this one out. We'll call this one g of x equals x minus 1 over x squared plus 2x plus 3. And turn this one off. And you can see as we approach the value of 4, so here's where I'm approaching. As I approach 4, it seems to me when I look on this table here that it's like 0.11111. Now, what is 0.1111? It's 1/9. So you can see that's true. And again, if you wanted to use the table, you could. Specifically, we're looking as x closes in on the value 4, so I could do like 3.9, 3.99, 3. And I'll do 3 9s, and then I'll do a 4. Do kind of the same thing. 4 plus 1,000th, 4 plus 100th, and 4 plus a 10th. And just like that, you can see that it's approaching the value of 1/9. And now number 3. On this problem, notice it's a polynomial divided by another polynomial, which we call rational. But if I directly substitute in -3, I have a problem. If I substitute in -3, I would have -3 plus 3, which is going to equal 0, and you're not allowed to divide by 0. So this is one that we would need to factor first. And so the numerator, I'm going to use X method factoring. I'm going to say this has an A value of 1, a B value of 1, and a C value of -6. And so when we learn how to do X method, this was lesson 03 or 1-0, if you will, the very first lesson of the school year. You learn you multiply A times C, we got -6, and the B value was 1. So we're looking for factors of -6 that add up to 1. When I taught this lesson, I said 2 variables, M and N, that multiply to give you a product of -6, that combine together to give you a sum of 1. I know the numbers are going to be 2 and 3. To make it be a positive 1, it would have to be 3 minus 2, and you can check it. -2 times 3 would be -6. So those are my 2 numbers. What we would do next is you split the A term's power. And so we'd have an x to the first, or 1x to the first minus 2 times 1x to the first plus 3. And if you happen to have an A value that's greater than 1, you would have to do bottoms up step. But I don't this time. So I'll just leave it like that over x plus 3. So this is an equivalent expression to this limit here. And you can notice that I could simplify these factors. And so I'm basically saying, what's the limit as x approaches -3 of x minus 2? And using direct substitution, we'd have -3 minus 2 more, which is going to give us -5. Now let's go check out this graph. Turn it off. We'll call this one h of x. H of x will equal x squared. This will be over x plus 3. X squared plus x minus 6. So it looks like a straight line as we approach the value -3. Let's see, -3.01. Oh, I'm doing this backwards, sorry. -3.1, -3.01, and then -3.001. Okay, so I'm getting closing in on the value -3. You can see it's undefined. That's because you're not allowed to divide by 0, so the function itself is undefined. But as 2.999, let me get these in there. 2.99 and then -2.9. So you can see that these values are closing in or approaching the value -5. It would be an open circle in there. Let me get this. I got to zoom way in. Right there, you can see it's an open circle. It's undefined, but that doesn't mean the limit doesn't exist. That means h of x might not exist there, or this function right here won't exist at -3. But graphically, we see that the limit does exist, and that limit was -5. All right, now we said in lesson 12.3, we're going to look at tangent lines and velocity. If you want your Desmos calculators, I was just using a blank one, but you could scan that QR code and get right there. So some words we'll get is a tangent line, instantaneous rate of change, difference, quotient, and instantaneous velocity today. The tangent line, I want to talk about that first. It's kind of like this idea of that if you had a shape, let me just clear these out of here. if you had a shape such as like a circle, let me use a circle real quick. We'll just say the circle has a radius of 5. A tangent line is a line that touches another object and it only touches it exactly one point and then goes off. So it doesn't cut through it. So here would be something that's not a tangent line. Specifically, we'd call it a secant line. A secant line would be a line that cuts through an object and hits the object 2 separate times. So 1, 2. Since it cuts through, that would be a secant line. A tangent line, however, is a line that touches an object just exactly at one point, just like that. So let me give you another example of a secant line. Y equals x. This is a secant line that cuts through the shape 2 different locations. However, if I were able to shift this line over just to the perfect spot, let me do it this way. R equals cosine theta. We could come up with an equation that would be a secant line if it would just barely touch it. Excuse me, that's a secant. A tangent line is if it were just barely touching it. So as we started looking through this, we would have to shift this value over just so it barely touched that circle, which we're going to learn how to do today. So this one, if I start, whoops, I meant to do +2. You can see we can get closer and closer saying, all right, so it's got to be something that's a little bit closer, but as I zoom in, I find out it's still secant. Right now, what I'm doing is guess and checking. Today, we're going to learn the math to do this exact. So let's get started with lesson 12.3. It says this: for an instantaneous rate of change. The instantaneous rate of change on a graph is given by, or the slope here of a point is given by the limit as h approaches the value 0, the limit of f of x plus this h minus f of x divided by h. Now, this means that as h gets closer and closer to 0, you can find how fast the graph is changing, whether going positive, negative, or staying constant at the point x comma f of x. That's the x, that's the y, x, y, and the slope m of the tangent line. That will be the slope of the tangent line. So when we take a look at this problem, I have here the graph, and I've shown you, here's the secant line. It's touching this parabola at just one point at 2, 5, and it's going through just exactly. And so what we're going to do is find the slope of the line at this graph at 2, 5. So to solve this, we're going to use that formula that was just shown on the previous slide, that the slope is going to equal the limit as h approaches 0 of the function f of x plus that h value minus f of x all divided by h. That's the formula we're going to use. So if I want to find this value at 2, that means my x is 2. If you plugged it in, you'll see the y is 5. 2 squared is 4, plus 1 more is 5. What I would do is I'll substitute in the values. So I'm looking for the limit as h approaches 0 of, and now f of x, so f of 2 plus h minus f of 2 divided by my h, which is ultimately going to be 0 or approach 0. So I'm starting here. So now what I'm going to do is substitute these into the equations. And this, honestly, using this formatting, I should call this f of x rather than y, or I could say y parentheses, but that would look weird. So I'm going to change that just to f there to make sense of this. So what I'm going to do is I'm going to plug in 2 plus h. And so this will equal the limit as h approaches 0 of, when I plug in the 2 plus h, I'll have 2 plus h quantity squared plus a 1, and then minus, and now I'm going to plug in the 2. So a minus, I'm subtracting this whole f of 2. When I plug in the 2, I'll have 2 squared plus 1. Now, since it's a positive, I don't need to use parentheses, but I'll go ahead and put them around that 2 squared plus 1, and then I'll close that bracket, all divided by h. And so now it just becomes a game of simplifying this. What do I have here is 2 plus h times 2 plus h. We can FOIL that out right here. 2 plus h times 2 plus h. When I FOIL this out, let's see, we have 2 times 2, which is not 2 times 2 is 2, is 4. There we go. 2 times h is 2h. H times 2 is another 2h. and then h times h is h squared. So this limit will be, and I'll write this here in purple, be 4 plus 2h plus 2h. Right there is 4 h's plus 4h plus h squared. And then we're going to subtract 4 squared plus 1. Subtract, not 4 squared, 2 squared is 4 plus 1, which means we're going to subtract 5. All this is over h. So now if I want to simplify, you might be thinking, is there a shortcut for this? Yes, we will learn there is a shortcut. This will end up, when I combine my like terms, here I'm going to have an h squared plus a 4h, and then I have a 4 minus 5, which is basically -1, all over h. And I just realized I forgot to add this little 1 right here. This little 1 that was right here needed to add in plus 1 here, plus 1 there. And so ultimately, I messed up on this. Let me take that away. This 4 gets simplified with this 4, and this 1 with this 1. There we go. And so now if I solve this by factoring, we could say that this is equal to the limit as h approaches 0. What I'm going to do here is a GCF. In the numerator, we have an h that's common. So it'll be h plus 4 over h. And now I can say, okay, these h's simplify with one another. So this is equal to the limit as h approaches 0 of h plus 4. Now that I have this as a polynomial, I can substitute in directly and determine that the slope will equal 4. M is the slope. Like this whole time we were saying m equals this, m equals this. This is the slope. And so our slope here equals 4. And so this tangent line would have the slope of 4. You could write the equation of this line if you use point slope form as y minus the y value, which is 5, equals the slope 4 times x minus the x value of 2. This is using the form y minus k equals m times x minus h, where this is your h and k. So this would be the equation of the line right there. And you could distribute this out if you wanted to write it in y equals mx plus b slope intercept form. But there it is, the equation of the line. They wanted the slope. We got the slope as 4. So now that you've seen how it works in long fashion, I'm going to let you try this one time, going about it the long way to check your work. And by the way, I guess from here, I could have, let me just show you graphically that we did get the correct answer. It was y equals x squared plus 1. And we're saying the equation is y minus 5 equals 4 times x minus 2. When you look, certainly as it is, this line, the blue line, the red line just barely kiss right here, but I only touch one time like that. They don't cross over to make it this a secant line. A secant line, again, would be something that went through multiple times, kind of like this graph here. That would be a secant, but this right there is a tangent line. Now I'll let you work on this one. Pause the video if you need more time. All right, example 2. Let's talk about finding the equation that would represent the slope of the graph at any point in time, not just maybe the point 1, 3 like this picture or the point -1, 1. Let's just talk about how would I find the slope at any one point in time. So I'm still going to use that same formula that we were given at the very start of the lesson, that the slope will equal the limit as h approaches 0 of f of x minus h minus, excuse me, that's a plus, f plus h right there, minus f of x divided by h. You can see now that my formula, it's the same one I used on example 1, and it's the same formula given here as the instantaneous rate of change. So what am I going to do this time if I don't have a point to plug into? Well, I'm still going to plug this into my equation. So when I plug in here, I will have the limit as h approaches 0. And what I'm going to plug into my equation, again, they call it a y, we could call this f of x, is I'm going to substitute in here x plus h, quantity squared, plus 2 times x plus h. And then we're going to subtract f of x, which means I need to subtract this whole equation. So I'll put in these brackets to make sure I subtract the whole equation. But just plugging in an x in there. So x squared plus 2x, all this over h. And now we go to simplify. So I will FOIL again over here, just like I did in the last problem, FOIL. We'll have x plus h times x plus h. When I FOIL that out, we will end up with x squared plus x times h, which I'll call hx, plus another hx plus h squared. That cannot be reduced. So we'll say the limit as h approaches 0, that front portion will just be x squared plus 2 hx's plus h squared. That's this front portion. And now I'll distribute this. Let me switch colors so you can see I'm now distributing this plus 2x plus 2h. And then finally at the end, I will need to distribute the negative through. Minus x squared minus 2x. Now all of this will be over h. So now if I go to simplify, I can say, okay, I see I have a positive x squared and a positive x squared. Those will simplify together. I have a, let's see here, a positive 2x and a negative 2x. Those will simplify together. And so it seems to me that the limit as h approaches 0 would be h squared plus 2hx h squared plus 2hx plus 2h, all divided by h. Again, I have a common denominator, or common factor in the numerator, a greatest common factor of h. So I can simplify this by saying this limit as h approaches 0 is equivalent to, if I do a GCF here, h I would divide out, so I'd have h plus 2x plus 2 all over h. And we can see that these h's would simplify with one another. And so now I'm saying, what is the limit as h approaches 0 of h plus 2x plus 2? I do a direct substitution at this stage. If I do a direct substitution, because this is now polynomial, I get 0 plus 2x plus 2. And so since this is my slope all the way down, my slope, I've now come up with my slope. And really, this is more than a slope. This is going to be the equation at any point in time. So that looks like a slope here. What that means is the slope itself will be 2x plus 2. The slope will be 2x plus 2. So whatever x value you choose, you will be able to find your equational line from there. Again, if I wanted to use the equational line using point slope form, that's supposed to be a k equals m times x minus h. Okay, now let me show you graphically what's going on here. Now that we know the slope, what I'm going to do is I'm going to graph this function here as given y equals 2x, no, sorry, x squared plus 2x. And that's the function itself. And we said that the tangent line here, the slope, I should say, the tangent line, or the instantaneous rate of change can be determined using the formula m equals 2x plus h. But here's what I'm going to do. I'm going to substitute an h in here, and I'm going to get two variables, h and k. And to make it a slider, I got to say like h equals 0, k equals something. Okay, so what I have in here is the slope, but instead of using the value x, because x is reserved for this x-axis, I'm going to use the letter h. So at any point in time, what I should have is this tangent line that's going to go through the point using this as a model, using h and k, y minus k equals m the slope of the tangent line times x minus h. And one more time, looking at this graph isn't exactly accurate. It should go through the origin, which it doesn't. This one does. Okay, as long as I line up this on any point that hits this parabola, you will see the tangent line at that point. Now, this calculator will automatically calculate it for us. And so I'm going to get a table here so we can see the points on this graph, and we're going to find tangent line. So for example, if I want to find the tangent line through the point 2,8, what I'm going to do is change h to be 2, k to be 8. And what happens is this purple line, because we had the formula typed in, it's programmed in like this, you see that the tangent line would come through right here, and the slope of the tangent line would be 6 at the point 2,8. Now, what if we wanted to find what's the slope of the tangent line at 1, 3? Well, I would just change this to a 1 and this to a 3. And now you can see, according to this formula, that the slope would be 4 at the point 1, 3, which is what we have over here. The slope is 4 through the point 1, 3. Let's check this point. When we look at left 1, down 1, you see that the slope is constant, meaning it has a slope of 0 through the point -1, 1. And so this represents it all the way around. If we wanted to find another point, like say this one right here, it looks like to me that's left 3 units, up 3 units. You can see left 3 would go up 3 right there. If I wanted to try that point, -3 and 3, you can see that the slope of this line would be -4, the slope of the tangent line going through the point -3, 3. Now this would work for everywhere as long as you're choosing a point that's on the graph. If we get a point that's not in the graph, obviously now this would not be calculating a tangent line, but as long as it's a point that's on the graph, which like -3, 3 was, this little calculator over here, the way I designed it would work, where I typed in the equation. I just started off with the equation itself. Once I hit table, it changed it. I just did y equals x squared plus 2x here and changed it to a table. The equation of a line and point slope, and I added the variables h and k and m to calculate the rest. Now, you have one. You can try pause the video if you need more time. You should be able to, if you want to use digital, the technique I did right here, or you can go through the algebra as we've shown using limits. Now let's talk about average velocity. If a position is given as a function of time for any 2 points in time, A and B, the average velocity is the change in the distance, that's basically the y values at time B and at time A, divided by the amount of time change, which would be B minus A. So if you want to find average velocity, that's the formula we're going to use. So it says in the physics experiment, a ball is catapulted upward. The height of the ball is represented by this equation, where t is in seconds and the height of the ball is measured in feet. What was the ball's average velocity between these 2 times? So the formula we just had said that the average velocity, which they say t subscript avg for average, is equal to f of the second time, which would be 2, minus f of 1, that's the change in distance, divided by the time change between the 2. So as I plug in these values, let's see, f of 2, I'm going to use the calculator just to help us out here, this time just for calculations, not trying to go through the whole picture. So the equation here is f of t equals -16t squared plus 95t plus 15. And I'm just going to get a table out real quick. And specifically, we want to know the difference between time at 1 second and time at 2 seconds. I don't need any of these other times here. And so what I'm getting mathematically is f of 2 would be 141 minus 94. And 2 minus 1 is 1. It looks like a negative sign. Let me take that away right there. Okay, and so when I subtract that out, 141 minus 94, we see it's 47. And so the average velocity is 47. And this would be, since it said in seconds and feet, this would be feet divided by seconds. Now you might be wondering, how did I get that unit? Well, because these values were in feet, these values were in seconds, And so it's feet divided by seconds. That's how the units would work. All right, and this is a positive change right now. This would be positive. Let me go here. Between 1 and 2 seconds, this graph is going, as you can see, it goes up 47 feet per that 1 second. All right, now it's your turn to try. Here's your equation. Notice it's very similar, just slightly changed. This is the effect of gravity, if you're wondering. And I want you to, this would be the original height. That's kind of its velocity moving upwards. And I want you to solve between time of 1 second, 3 seconds. Pause the video if you need more time. All right, now let's talk about instantaneous velocity. So very similar to the rule we were looking at earlier, when we were looking at the instantaneous rate of change, the instantaneous velocity will be found by using the limit as h approaches 0 of f of t plus h minus f of t all divided by h, where v of t is a instant velocity. So what we found is the instantaneous velocity of function f over time, provided that the limit exists. So let's take a look at example 4 here. It says tourists standing on a 300-foot tall viewing tower often drop coins into the fountain below. The height of the coin falling from the tower after t seconds is given by this equation, where this is the height, original 300 minus 16t squared. That's the effect of gravity on any object. And feet, that is, feet per second squared. It says find the instantaneous velocity, v of t, of the coin at 2 seconds. And so here's the idea. We want to find the instantaneous velocity, and according to the formula in the previous slide, that would be equal to the limit as h approaches 0 of this function h of t, which is not a fraction. So let me write this as 300. Oh, no, I am right. Fraction, we need to write f of, what we're looking here is h of t plus h. I'll just write it out in function notation first, t plus h minus h of t. That's going to be our formula. So let's plug in and see what we get here. The limit as h approaches 0 of, okay, if we plug in a t plus h, we get 300 minus 16 t plus h quantity squared minus, and now I'm going to use these other brackets here, h of t. Should be just 300 minus 16t squared. All of this would be divided by h. Okay, so now let's go through simplifying. Whoops, that's not what I want to do. All right, so if I go through to simplify, what I will have here, the limit as h approaches 0, we will have 300, and I need a FOIL. So let's figure out what t plus h times t plus h is. So when I FOIL this, I will have t times t, which is t squared, t times h, so I'll say ht, plus another h times t, another ht, plus h times h, which is h squared. So we would have 300 minus 16 times t squared minus 2ht, no, plus, not minus, I'm sorry, plus 2ht plus h squared. And then when I distribute this next portion here, I'll distribute the negative through here, minus 300 and minus a negative would be a plus 16t squared. All this divided by h. And so right away, I can see that some values will simplify here. We have a 300 minus a 300. That'll go away. And when I distribute this through, I'll have a minus 16t squared, and I have a plus 16t squared there. So these two values, when I distribute that, will simplify. And that would leave us with the limit as h approaches 0. When I distribute here, I'll have a negative 32 ht and a negative 16h squared all over h. So I see that there's a common denominator here, or not a common denominator, sorry, common factor in the numerator. So this would be equal to the limit of h approaching 0 by GCF that h out of there, greatest common factor. I could actually pull out a negative 16 as well. Negative 16h. That would leave me with, if I divide this by negative 16h, that would leave me with positive 2t. And then since I pull out the negative 16, it'd be plus 1h, plus 1h, all over h. We can see here that these h's will simplify with one another. And so I can just directly substitute this in. I guess I didn't have to take out the h because I'll end up distributing this right back here. It'll be a negative 32t negative 32t, and I'm putting in a 0 here for h, so it'd be a negative 16 times 0, which that simplifies. And so it seems to me the velocity vector via t will equal, not the vector, I'm sorry, the velocity function would equal negative 32t. Now that's the equation here. So if I want to find it at 2 seconds, what's the velocity of the coin after 2 seconds? It would be negative 32 times 2, which is equal to negative 64. Like I mentioned before, this is feet per second. That's feet, and this is per seconds. So this would be negative 64 feet per seconds. Would be the velocity at time 2. Now, if you are wondering, what does this velocity vector have to do with this? This is the tangent line. Let me make that connection for you. If we looked at h of t being 300 minus 16t, and I'm going to set this to where the highest or the lowest value is going to be negative 10, and we're going to go up to 350 so we can see above this graph. There we go. And let me change the x-axis. We don't need to see that far wide. We'll say from negative 5 seconds to positive 10 seconds so you can get an idea of this parabola here. What we found out is our velocity vector via t equals negative 32t. And so that's the speed at which you can find that the value is falling. So at 2 seconds, we said it's negative 64. So at 2 seconds, which is right here, the slope of this line at 2 seconds would be negative 64. Let me kind of show you here. Y equals negative 64. And let me change the color here in this tangent line so you can see what I'm doing. Negative 64x. And if I want this to be at 2 seconds, and at 2 seconds it looks like this graph has a height of, if I get there exactly, 236. So to be up 236, I'd say minus 236 there. And x to go right 2 needs to be minus 2. You can see that is the tangent line. So it's falling at 64 feet per second at that point. That's right 2 units, meaning 2 seconds, and at a height of 236, because that's what the height would be at that point. You can see how it's a tangent line. That is the instantaneous velocity. So that's how the graph there corresponds with what we were learning about tangent lines. The tangent line is the instantaneous velocity or rate of change at that point. All right, example 5, instantaneous velocity at any point. The distance a bumblebee flies along a path is given by this function p, where t is given in seconds and the distance of the bumblebee from a starting point is given in inches. That means p is calculated in terms of inches, p of t. Find the equations for the instantaneous velocity of the bumblebee at any point in time. So to do this, what we would say is that we know that the limit, so let me back up here, the velocity will be equal to the limit as h approaches 0 of this function. So I'll say p of t plus h minus p of t all divided by h. That's the formula we're going to use here. So plugging in my values here to solve for this limit, it seems as we're going to plug in t plus h in here. And so we'll have 12 times t plus h minus 6 times t plus h cubed, quantity cubed. That'll be fun here in a moment, plus 1. And then we will have minus, and I'm going to throw in here a different color. Now we would just have this equation p of t itself, minus 12t minus 6t cubed plus 1. And all this will be divided by h. Now, before I go too far in trying to simplify or trying to FOIL this out, I can state confidently that this plus 1 and this, when I distribute here, we're going to distribute all the way through here. This will become a minus 1. The plus 1, the minus 1 will cancel one another out. And so we'll see what happens to the rest of the equation as we go. I can see that I'll have a 12t here, and I minus a 12t there. So I'll go ahead and remove that. And we will have to, I would call it a FOIL, but it'll be more than a FOIL on this portion. So now let me rewrite what we have here. We have limit as h approaches 0. Here I will have 12h. The 12t minus the 12t are already canceled out. So I have the 12h minus, okay, and now we need to do what I would call a FOIL, but it's not truthfully even a FOIL, it'll be more than that. I'm gonna write it over here. T plus h times t plus h times t plus h. And it gets multiplied by -6. That's what cube looks like. It happens 3 times. So we could multiply here the first time through. The -6 will just distribute to this first parenthesis. So I'd have -6t minus 6h. And then this would multiply. If I wanted to FOIL out this end, I would have t squared plus an ht plus another ht is going to be 2 ht's if you've seen me FOIL a few times, plus h times h, which is an h squared. So now I'll multiply these two groupings. I will have here a -6t cubed minus 12ht squared and a minus 6h squared t. Here we have minus 6h squared. No, that's off, sorry. T squared, minus 6ht squared. Here I have, this will be a minus 12h squared t. And then finally, right there, minus 6h cubed. When I combine my like terms, this is going to be -6t cubed minus 18ht squared minus 18h squared t minus 6h cubed. Okay, so that's what's coming next in this middle portion right here. So we have a minus 6t cubed minus 18h squared t minus 18ht squared minus 6h cubed. Finally, when I distribute this portion over here, we would have minus a -6t cubed, which is a positive 6t cubed, and all this divided by h. All right, so let's see if we can cancel anything now. When I look at this listing in here, I see I have a minus 6t cubed and a positive 6t cubed. And then I also share an h all the way across. I could divide out a 6. I'll just put that in the front of the limit right here. So 6 times limit h approaching 0. I'm dividing everything by 6. And I will GCF this h out. So I've already taken out a factor of 6. So this will be left over 2 here. Minus 3. One of those powers of h is gone. ht. Minus another 3. This h is gone, so it's just t squared. Minus 6h squared. All of this divided by h. I can see that my h's get simplified, which means this is going to be equal to 6 times the limit. And now that that is a, I actually don't need to write the limit again. Now that this is polynomial, I can just do a direct substitution. 6 times the value of 2 minus 3, 0 times t, because h is approaching 0, so I'm substituting a 0 there, minus 3t squared minus 6 times 0 squared. So multiplying by 0, those values will simplify out of there. Let's see what we come up with. We'll have 6 times 2, which is 12. 6 times 2 is 12. And then here, minus 18t squared. That right there appears to be my velocity equation. So that would be v of t. V of t would equal 12 minus 18t squared. That's my velocity function at any point in time. And that's what we were supposed to find it for any point in time. And so again, if you wanted to relate this to the graph, like what does that do for me? Let me graph the first function here, p of t equals 12t minus 6t cubed plus 1. And we're saying the velocity vector, or the velocity function, I'm sorry, velocity function is 12 minus 18t squared. Okay, so when you look at them, they don't look alike at all, but given a certain point in time, if we have any certain value, I don't know if this will allow me to do a certain t, if that's going to throw off this problem. Yeah, it will. But what would happen is if we were looking at this and you wanted to know the velocity or at any point in time, let me just say like p of 3 here. Rather than do it that way, let me show you a table. Okay, so here's the values. So for any one of these points in time, if you want to know what's the velocity here at time 0, what's the velocity, what will happen is this graph at time 0 will show you what the instantaneous velocity is, or what the slope of that line is. So at time 0, it's 12. That means the line going through this point right there is 12. And if you're like, can you prove that to me? Yes, I can. Let me take that off for a second, velocity. And if I did y equals 12x, that's that slope. But to make it go through this point of 0, 1, I'll use point slope. So minus 1. And this minus 0. I know you don't have to have the minus 0. You can see that that is a tangent line going through that point at 0, 1. That is the slope of that line going through. It just touches it one time, it goes perfectly through it. Just the same, if let's say we wanted to find the tangent line or the slope here at 1, 7, what I would do is I would come over here and say, all right, at 1, 7, it looks like the slope would be -6. So if I did -6 at the point the x was 1, the y was 7, you can see that I have a tangent line coming through right here. I'm using the value at 1. Here, there's 1, 7. That's the position. This function here is the position function. This one right here, it's what you'll learn is called a derivative. It's telling you the slope or the instantaneous velocity. Its velocity at 1 time of 1 second is -6. So when I plug that in, using this as the position and -6 is the slope, you see that the value works out perfectly for a tangent line. So with all that, that's kind of the extra. That's how the graph looks. Let you try this problem here. Stop the video if you need more time.